Hola, buen día a todos. Good morning, everyone. Vamos a comenzar la sección 1, la sesión oral 1 de COMM 1 BTS, Communication Service and Broadcasting. Tenemos 4 presentaciones, todas muy interesantes. Algunas de ellas tocan diversos topics, no son uniformes, pero son todos muy interesantes. Como primera presentación tenemos on the Energy Efficiency of One Lawyer CSO Rate Splitting Multiple Access. Es un trabajo interesante con un enfoque a un caso particular, pero bien generado. Y bueno, se abre a la presentación y estaremos atentos para las posibles preguntas luego. Tenemos 20 minutos máximo. De ello, lo ideal es tomar unos 15 minutos y dejar unos 5 minutos para preguntas o menos. Pero bueno, adelante. Lo único que tienen que hacer es igual que siempre, que si fuera Zoom, levantar el share screen.
Okay. Good morning. Thank you, Fernando.
It's on the screen now.
Okay. Hello, everyone. I am Wilson Souza Jr. from State University of Londrina at Brazil. And today I'll explain about my developed work accepted in COMM entitled On the Energy Efficiency of On-Layer SISO Rate Splitting Multiple Access. Its work comes from a partnership between the Signal Processing Laboratory at State University of Londrina and the University of São Paulo, both in Brazil. Herein is a summary of our presentation today, which will follow by the motivation of the work, explanation of the rate splitting multiple access, the adopted problem which we are working on this paper, the obtained numerical results, and the conclusions with future suggestions. So let's talk about the motivation of the work. In the future networks beyond 5G, 6G, so on, massive machine-type communications will be one of 3 major scenarios due to the exponential growing number of devices. And a typical projected scenario is IoT device connected in the network as instance. Besides, the energy efficiency problem is a primordial problem, and it is regarded as an essential problem for future networks due to the high data rates and a massive number of the users connected. Then it should be carefully studied in order to develop a green and sustainable wireless network. Furthermore, rate splitting is an emergent multiple access scheme that has the potential to support multiple users, and its work we are interested to know if it can provide higher energy efficiency than the other methods are already known in the literature. So the findings obtained can be summarized as the following. The first one, we formulated the energy efficiency problem as an optimization problem. So we proposed an algorithm that maximizes the energy efficiency. We also confirmed that the rate splitting is essentially projected to operate in MIMO or massive MIMO scenarios, where the base station is equipped with many antennas on active antennas. We also extended the results present in the reference 1.4 to energy efficiency case. Okay. So, as previously commented, rate splitting is an emergent multiplex scheme that can bring some advantages with respect to the other methods as NOMA and OMA, for instance. But what means a multiplex scheme? Well, multiplex scheme is, in resume, methods to allocate users in resource blocks like time or frequency in order to communicate with the base station simultaneously. So, NOMA, as instance, is a non-orthogonal multiplex scheme where the users are allocated on the same bandwidth but are different in the power domain. And OMA is our orthogonal multiplex scheme like TDMA or FDMA, frequency division multiplex, time division multiplex, where the users are in the time or frequency respectively. So the idea behind the rate splitting is split the message intended to users into basically two parts, the common message and the particular message. And by doing it, the inter-user interference can be mitigated and the complexity in detection per user can be substantially reduced. And in general, it can achieve a higher sum rate and a lower complexity detection per user. Okay, so in our work, we consider the following system model. Well, we consider a single cell network operating in a downlink with k users. So we adopted the single input, single output, where the base station is equipped with just one single antenna. And the only layers rate splitting will be adopted to simplify the analysis on that for higher layers, it can has elevated complexity, and figure 1 here depicts the architecture of the on-layer rate splitting procedure, where we have k users, and the message of the k users will be split into common message, as said, and it will be jointly combined. So the particular messages that are independent will be transmitted as well. At the receiver, the aim is our user should firstly decode the common message and afterward recover its private message through the successive interference canceller procedure, as known as SIC, that it is also utilized in the NOMA assistance. Okay, here I'll talk about the adopted problem. The energy efficiency is in general defined as the ratio of the spectral efficiency over the whole power consumption, and it is given by the equation 1, where R sigma is the sun rate, PC is the consumed power at the base station, PTX is the power for transmission, while Varho is the inefficiency of the rate frequency. And in general, the energy efficiency is a quasi-convex problem, and it has been proved in our work. It is very important. We will deal with optimization problem, which will be detailed as follows. Specifically, the optimization problem can be formulated as follows in equation 2. The problem P intends to maximize the ratio with respect to P, C, and PTX variables. And the problem in question has 6 constraints. Equation 2A means that each user should have a minimum data rate. Hence, the sum of its privated message and common message should be greater than R min, which will is a parameter of this to be defined. To be indicated that the attributed power to the common message P0 should be greater than a certain value, that all the user should be able to decode the common message. To C indicated that the sum of the attributed power to the common message and the private message of each user should be less or equal to the utilized power. 2D indicated that the sum of the common message attributed to each user is less or equal to a certain rate denoted by M. 2E and 2F indicated that both the allocated power and the allocated rate should be greater or equal to 0, and the utilized power as well. Here, the sum rate has been written as the sum of the common message given by C and the private message given by V. Figure 2 shows the architecture of the adopted problem, and it's not worth that the optimization problem P has been subdivided into 3 sub-problems, where the P1 is the power allocation problem. So we have the problem P, and we have some fixed inputs as P0, C, and PTX. Our goal is obtain an analytical solution to P, which means the private power allocation. Once obtained the solution, we solve P2, where the fixed inputs are P0 and PTX. Is constant, so we obtain C, the optimal allocation common rate. We aim to solve the problem P with P0, P, C to finish PTX in P3, which means the optimal transmitter power selection, which will maximize the energy efficiency. It's not worth that Young et al. Already provided a solution to P1 and P2 in the work entitled Downlink Sum Rate Maximization for Rate Splitting Multiplexes. Hence, our goal is to solve adequately P3. Okay, so let's talk about the numerical results obtained. Figure 3 shows the 2 figures. TA is about the average energy efficiency, and B is about the average sum rate. The numerical results have been obtained through the Monte Carlo simulation, where the system model parameters are detailed on our paper. So we adopted NOMA and OMA as benchmarks. Here we consider a lower bound and our upper bound for rate splitting. So the upper bound is when there is no interference between the privated message of the users, and lower bound means that the worst case scenario where there is interference. We can see that rate splitting in upper bound given by the blue line can outperform all the other schemes. However, it is a hypothetical scenario which cannot be developed in practical situations. Also, we cannot see that in SISO scenarios, NOMA given by the yellow line outperformed the lower bound rate splitting given by the red line, which confirms that rate splitting is a multiple access scheme developed to work in the minimum scenarios. It's not worth that the proposed algorithm can provide maximum energy efficiency, and the rate splitting operates as expected. The maximum energy efficiency in solid line can conduce leads a constant sum rate after a certain threshold, while a maximum sum rate in dashed line leads a poor energy efficiency. This is due to the algorithm is able to select a PTX less or equal Pmax for maximize the energy efficiency. Different lie for the maximum sum rate case where all the power is utilized. So we can conclude that the single layer rate splitting schemes operating over the worst case scenario SISO can be promising, and if well deployed, can achieve greater performance than the other multiple access schemes as NOMA and OMA, for instance. And as future works, rate splitting operating in massive minimum scenarios can be adopted, and resource allocation can be further exploited. The reflecting intelligent surface added by rate splitting scenarios can be exploited as well in order to better describe the operation model of the system and all possible gains. On that reason, has calling so many attention in both industrial and academical scenarios. So I would like to thank you to everyone, and to CNPq and State University of Londrina. And here are the references utilized. So thank you, everyone.
Thank you very much for the presentation. There are questions from the audience. I have no one in the chat. We have some minutes. I want to ask one. What do you think about using the rate splitting multiple access for new generations telecommunications, for example, 6G or something like that?
Mm-hmm. Well, I think that it's very competitive with NOMA. Both schemes are non-orthogonal multiple access, but I think that rate splitting can be promising in terms of complexity of detection, because each user should realize just on a single time the seek procedure. Different line of NOMA as it stands, where the strongest user should realize n times. So I think that in terms of complexity, it can be promising on that it can improve the outage probability as it stands.
Okay. Okay, thank you very much for your presentation and good work. Thank you.
Thank you. Welcome.